So, good afternoon, everybody. First of all, I would like to thank the organizers for inviting me to talk today. And I've been asked to give you an overview of our recent work on ISM and unclassified relations. So this talk will pretty much divide into two parts. In the first one, I will highlight the power of ISM relations to try to better discriminate between the effect of nature and nurture in galaxy evolution. And on the second part, I will switch a little bit here and try to convince you on the power of finally putting galaxy of all morphological types on the same level of classifications. So these slides pretty much summarize the state of the field when we talk about dynamic when we talk about gas and dust state relations. You see here how the H1 content, H2 content, and dust content normalized by the stellar mass of the galaxy varies with a bunch of galaxy properties, stellar mass, surface density, and color. And you can clearly see that all state relations give you pretty much the same picture, that when we move from low mass, disdominated, star-forming galaxies to high mass, bulk-dominated quasar systems, we find a monotonic decrease in the amount of gas and stars compared to the stellar mass. Of course, while qualitatively this decrease has been known for probably half a century, the ability to finally quantify this for representative sample of galaxies has turned out to be really powerful. On one side, the ability to define normalcy provides a very strong constraint to theoretical models. Here you find several examples of how now H1 state relation provides us a way to check that our theoretical models are scaled correctly when it comes to H1 content. But of course, the ability to define normalcy also allows us to go a step further. Once we have understood what is the typical gas or dust content in the average galaxy in the local universe, we can now split galaxies, for example, by environment and go a step further. So in this slide, I would just want to give you a taste of particular the power of the combination of not only gas but also H1, H2, and dust relations when it comes to environmental effects. Here, what I'm just showing is the variation of the dust to gas ratio as a function of stellar mass when we move from field galaxies to cluster galaxies. And I want you to just focus on the central and the right-hand panel. Here, what is interesting to see is why, when we move from the field to the cluster galaxies have at the same time a lower H1 to dust ratio and a higher molecular hydrogen to dust ratio compared to field systems. And this is pretty easy to understand because it tells us that the H1 is the component that is much more affected by the environment, then it comes the dust, and then it comes the molecular hydrogen. And this is a fantastic tool to then test theoretical models because it simply shows us that the effect of the environment is consistent with differential stripping acting outside in, and these trends are just a consequence of the fact that the H1 is the component of the galaxy that is much more extended in the disk, then it comes the dust, and then it comes the CO. But this is just to give you an highlight of what has been the recent work on this field, but of course, as every other field in galaxy evolution, we are facing current challenges. On one side, we are still struggling in identifying what are the physically driven relations, as already been discussed this morning. The fact that the quantities correlate, in particular from the integrated point of view, doesn't mean that there is a physical link between the two of them. After all, we expect that bigger galaxies have more of everything, so a linear correlation doesn't tell us much. And on the other side, a great part of the work on environment-based state relation is so far based on cluster galaxies. Clusters are great, are fun, but they are not representative of the environment in the local universe. The vast majority of galaxies live in groups, and so what we really want to do is to look at the effect of nurture in groups. And of course, for these two, let's go back. Yeah. For both these two questions, the struggle has been the number of statistics. While we made a lot of progress in getting representative samples for both molecular hydrogen and H1, we are still limited to a few hundreds, which means that when we want then to dissect the state relation, we are lacking statistics to really look for secondary trends. And while for the H1 and the dust, we probably have to wait several years to make progress, in terms of H1, we can actually make progress now thanks to the combination of optical surveys like the Sloan Digital Survey and Glide H1 survey like alpha-alpha. And using a technique that allows us not only to look at single detections, but also to trace the information that is stored in the detection from an H1 blind survey. And this is via the stacking technique. What we actually do is we select a sample from zone, let's say based on stellar mass, then we extract the spectral H1, regardless whether the galaxy is detection or non-detection. We beam them depending on which quantities or which secondary trend we want to look at, and then we get an average H1 content for the family of galaxies we're interested in. And this allows us to move a step further because we can play with a lot of statistics. And in the next couple of slides, I want to give you a taste of the power of this technique. Now, first of all, dissecting scalar relation and trying to isolate, to discriminate between primary and secondary dependencies. Now, here I'm back to the original scalar relation that I showed you, gas fraction versus stellar mass, and gas fraction versus color specific star formation rate. What I've done here is just split galaxies by stellar mass in the gas fraction color relation, and by color in the gas fraction stellar mass relation. Very simply, you can see that once we split by secondary quantities, very little difference is found in the gas fraction color relation, and the different relations pretty much follow the slope of the relation for the same sample, which is here highlighted in black. While when we split a fixed stellar mass by color, we see that the blue sequence in blue and red sequence in red spread across almost one order of magnitudes. And even more importantly, the slope of the relation, once we control by star formation rate, is significantly flatter than the slope for the entire sample. And this pretty much tells us that probably the relation between gas fraction and stellar mass is not really telling us a lot about the physics of what's going on in galaxies, just a byproduct of the relation between gas content and star formation rate, the so-called integrated Hellinger-Schmidt law, and the fact that when we are at low stellar masses, great part of our galaxies are in the blue sequence, as you can see here with this number, and this being pretty much all the galaxies are in the blue family. And when we move to high stellar masses, we have an inversion, and the vast majority of galaxies are quiescent. So we see that the black line is actually driven by the balance between the number of star forming and the number of quiescent galaxies that I have in a stellar mass D. And this, of course, tells us that this is probably not the best observational constraint to theoretical models when it comes to try to reproduce the gas content in galaxies. Of course, we can go on and play this bit further, and I just want to show you the power of this when we look at the environment. And we finally can have a look at the effect of the environment on the gas outside clusters. So these are, again, the same relations. The only difference here is that now I'm not plotting color, but I'm directly plotting specific star formation rate. And in this case, galaxies are plotted by environment, quantified in terms of velomasses. And you can clearly see that there is a monotonic decrease in the gas content, but the most important plot is actually the right-hand panel, and I'm trying to convince you that this is probably the more physically motivated one. And it's interesting to see that the fixed specific star formation rate, galaxies, when we move from pairs to clusters, have a decrease in H1 content by at least a factor of 10. And this shows that the H1 is removed on significantly faster time scales than the star formation sequence, with kind of add to the picture that also outside cluster, something that we already knew for cluster, but something that we didn't know outside clusters, the stripping of H1 is significantly fast, and then the star formation has to catch up. So, to summarize the first part of this talk, I hope to convince you that with scalar relation we can now move a step further and try to look at secondary relation and try to understand a little bit more about the physics that relates the global gas content and the galaxy properties. Of course, as I already hinted, for the future something that we need to take into account are the Cortese challenges, in particular in terms of number statistics and in terms of H2 and gas properties. We probably, I don't want to be pessimistic, but we probably have to wait a decade before being able to do this kind of studies in terms of the H2 for thousands of galaxies in the local universe. But of course, the main power in terms of scalar relation of the ISM has been the ability to put all galaxies, regardless of the morphology, on the same scalar relation. And this is something that now, switching gear in the second part of the talk, for historical reasons we haven't been so great at doing when it comes to dynamical scalar relation. Usually what we tended to do is just to look at pure disk and pure spheroids and try to look at the dynamical properties of galaxies for these two classes of objects. But now we know that when we look at the average galaxy in the universe, this is neither a pure disk or a pure spheroid. As you can see for this stellar mass function in the local universe, the red and the purple lines indicate the morphological classes that have both a bulge and a disk, at least based on photometry, and you can see that they dominate the number density of galaxies at least around above 10 to the 9.5. So this is really important to try to get a homogeneous picture of the effect of dynamical string relation on galaxy properties. And this is a field that has become extremely popular in the last couple of years, and one way to look at this is try to think that galaxies are not really lying on the same relation on a 2D plane, on a 2D relation, but they are probably related on a 3D plane that perhaps relates mass, specific angular momentum, and morphology or spin parameter. These are on one side theoretical grounds, of course, and it's something that has been investigated in the last couple of years with several works, for example, of Manowski and Fall and Obreshko and Drake in the last couple of years. Of course, these were very interesting works, and the main limitation is that they were based on relatively small number statistics and lossless spectroscopy. Now, in the era of IRSS surveys, finally we can try to move a step further and try to look at this scalar relation from the result point of view. And I want to present you in the last couple of minutes the results that were being obtained using the SAMI Galaxy survey. Now, Scott introduced this more in SAMI, so I don't want to spend too much time in reminding you what SAMI is, and I will dive immediately into the results. Now, these two plots show the relation between stellar specific angular momentum measured within one effective radius and stellar mass for a sample of around 400 galaxies extracted from the SAMI survey. Now, in the two plots, galaxies are color-coded either by visual morphology or by sensitivity. And you can clearly see that first, there is a decent correlation between specific angular momentum and stellar mass, as other people have already shown. And interestingly, the scatter of this relation is somehow related to morphology, either whether you classify it visually or by sensitivities. But of course, this is the observational way to look at this, try to link mass, angular momentum, and morphology. From a theoretical point of view, we should look at this in terms of morphology but spin parameter. And if we look at this using the lambda r parameter as a proxy for the galaxy stellar spin parameter, we find pretty much the same result. We find that the scatter is correlated to the spin parameter, which is not surprising at all. It's just telling us that when I fix the stellar mass, the position of the galaxy in this relation, it just depends on the balance between ordered and random motions to the dynamical support of the galaxy. Of course, this just justifies us to really try to investigate this concept of plane between stellar mass, angular momentum, and morphology or spin parameter. Here you see an example of different projections of the plane, and of course this suggests that the spin parameter should somehow be correlated to proxies for morphology. The interesting thing here is, for example, as some people have already pointed out, is that this correlation is actually not linear, and the interesting thing here is that when the surface index would tell us that all galaxies are pretty much the same bulge component, when we look in terms of spin parameters, we find a very wide spread in dynamical support, which again points towards the idea that we should probably move away from photometrically based morphologies and try to use kinematics to actually classify better galaxies. Of course, the other interesting thing in terms of stimulation is that the scatter of this plane is quite small, is of the same order of magnitude of the scatter that we find in the Tully-Fisher and Taylor-Jackson relation once they are pruned for either pure disk and pure spheroids. And this is really interesting and tied in with what other people have tried to, other simulations that other people have tried to look at to unify galaxies of different morphologies. Now, if we look at what is in general our roughly best fit for the morphology spin parameter plane, we find that the angular momentum is directly proportional to the spin parameter times the stellar mass at a certain power. And if we think how observationally we estimate these two quantities, we can actually express this as the stellar mass being proportional to a combination of rotational velocity and dispersion velocity. And of course, this is something that many people have tried to look, the relation between stellar mass and this combination of rotation and dispersion. And this is also something that we've investigated with SAMI before. And I want to conclude with just this plot that shows, again, a different way to look at the problem. Here I'm plotting stellar mass Tully-Fisher-like relation, a Faber-Jackson-like relation, and what you get when you combine rotational velocity and dispersion velocity. The point here is that Here I'm not doing any morphological pruning. Here I'm plotting all the galaxies that I got at that time with Sunny, and indeed you can see that the value Fisher and Taylor Jackson have a large scatter, but when we combine everything in terms of rotation and dispersion, we find a very tight relation with no pruning, which now we can interpret as consistent with the projection of the mass angular momentum in parameter plane that minimizes the scatter. So, to conclude briefly, I hope to have convinced you that now with IFS survey, in terms of dynamical stimulation, we should actually move away from looking at dynamical stimulation for separating morphological types and try to look at all galaxies together. Of course, in this field, this is a very young field, and we have a lot of challenges to face, and in my opinion, two of the most interesting from a scientific point of view are that one, all I've shown you at the moment is limited to within one effective radius, and this is a limitation because when we think about angular momentum, we expect from a theoretical point of view that the vast majority of the angular momentum is stored in the outer part of galaxies. And on one side, it's interesting that we already find this correlation within one effective radius, but going to the outer parts would be extremely important. And on the other side, of course, at the moment, we are always plotting everything against stellar mass, but we know from, for example, Kali-Fisher's work that probably the most fundamental quantity is the baryonic mass. And so it will be really important to look at this correlation in terms of baryonic mass. And of course, it will also make us possible to finally put together the field of ISM scalar and dynamical scalar in the same mass. And I will have to do that. Thank you very much.
Okay, we have time for 2 or 3 questions. The first one.
I can shout. So the relation between the angular momentum and stellar mass, fine. Is it? Do you have the same slope as the Ford relation? So 0 at first. Okay, I see you have something to say. Now the second thing I was wondering if you try to separate badges and disks in the same time.
Okay. To answer the first question, yes. To first order, we find a slope that is very close to the two-third that Romanowski found, that is consistent with what we expect from the analysis. But to be perfectly fair, I don't think I would trust the slope that we get at the moment, simply because we still have to understand all the selection function that goes in defining the set. So while the scatter is less dependent on your selection function, the extra slope, in particular when you begin by morphology, could be affected. Nevertheless, it's interesting that both in terms of the stellar mass, specific angular momentum, and in terms of the plane, we found the slopes that are expected from a theoretical point of view.
Okay, so question?
Again, about the scatter, in the case of the gas fraction relations,
yes.
It's very important, I think, to estimate the scatter in this correlation. The average could be biased by the selection effects, etc., by the time, Rosberg mark, etc. So, what are the scatters in these correlations? This is the first question. And the second is about the upper limits, the non-detections. In the case, for example, of early type galaxies, you know, most of them are not detected in gas. So you have only upper limits. So, how do you manage this question for the correlation that you are showing?
Okay, there are different points. The first one, let me clarify. So, this is based not on individual detection. This is based on stacking. So what we do, we select, let's say, in this case, we select all galaxies that have an UV minus R power of this quantity and a stellar mass of this quantity, and we stack all spectra. Now, if you see a point here, this means that the stacked spectrum is a detection. So we find signal also up to the early type galaxies. If you see, like in this case, a triangle, we don't have a detection even in the stacked spectrum. So this is the upper limit that we get from the stacked spectrum. But you can see it here, you have very few triangles. So this means that with stacking, you can actually probe the gas flow regime. So this is not affected in any way by non-detections. Of course, to answer the first part of your question, the stacking doesn't give you a way to quantify the scatter, because you get an average and that's it. But in this way, if you then select galaxies by a secondary quantity, you can actually have a feeling of the scatter. And this confirms what we get from individual detection, that the scatter in the gas fraction correlation is significantly smaller than the scatter in the gas fraction stellar mass relation.
Okay, there is no time for more questions, so next speaker, please.